Good afternoon, everyone. Welcome to my presentation at CMMSE 2026. My name is Aphinan Photun from Naresuan University, and our topic today is approximating solution of generalized pinball loss probabilistic support vector machine using neural network with unified smoothing techniques. This work was conducted alongside with my professor Fabian Wankiri and Yilka Abebele as part of the Deep Math AI research group. And here is the brief of this presentation. We will go through the introduction of this work first. This one is the classic supervised machine learning model, the support vector machine or SVM, that is used to find the optimal hyperplane that separate two classes while maximizing the margin between them. However, the classic hard margin formulation requires absolute separation of the two classes. This makes it difficult when we have to do it on real-world datasets that it have a very noisy data or outlier and anomaly. To beat this problem, we have the soft margin SVM that introduce a slack variable and use the loss function like the well-known one that is called Hing loss. To penalties, the margin violation make the SVM become the optimization problem in equation 2. And while the soft margin help the real-world data uncertainty for measurement and sampling error require a more robust approach. So probabilistic SVM or PSVM come to handle this. Instead of viewing data point as static coordinates, PSVM treat training sample as random variable with the expectation. The margin required are then become as chain constraint as it shown in equation 3, ensuring a sample is correctly classified within the specific probabilistic threshold. That means we can uh, use it as a hyperparameter that we want to probability that it will match this condition, how much we want it to match in this condition. And furthermore, by transforming this stochastic bound into the tractable deterministic counterpart, we can mathematically handle uncertainty directly inside the architecture as is shown in equation 4. And from this, it comes there's many approaches in this research area. For the first one is in the path framework, it translates this stochastic parameter into the quadratic programming, and the author approach from Poisson chain is address the native lags of probabilistic output in SVM by enforcing the truncated Gaussian prior and employing the expectation maximization algorithm to achieve a maximum uh, posteriori estimation. And more recently, the research have leveraged a recurrent neural network to map this probabilistic constraint into the KKT condition that's using the continuous time architecture like ODE to solve it. However, a critical struggle gap might remain that all of these existing methods rely on the loss heavily on loss function that either introduce several non-differentiable or completely ignore bidirectional noise. This creates an acute computational bottlenecks, establishing the immediate need for a smoother and constrained alternative to solve this problem. And from this, uh, let's we talk about the issue of this classic loss function. From the existence of existing of PSVM formulation, it's working on standard Hing loss, which exclusively penalty the data point that violate the margin boundary. It completely ignores the cluster noise or outlier that happen to sit safely on the correct side of the separating hyperplane. But in other words, we can say that it very sensitive to outlier, which is come up with a lot of noise, a lot of loss, which is not good. To solve this problem, we can shift it to auto loss like a pinball loss, but for this loss, it still have the problem in the loss of sparsity that as it show from this figure that when we does not make the support vector machine that when we compute the loss and that data point does not stay at the exactly the support vector is will compute the loss, so we will don't have we will have a lot of loss, and that is the problem. So our framework is shift to generalized pinball loss, or and is introduce a asymmetric penalty that account for noise on bottom side of the classification boundary and solve the sparsity problem. While the generalized pinball loss handle the bidirectional noise of the sparsity, it is introduced a several hardware bottleneck that is still non-differentiable. And from the chart structure, things where the derivative breakdown make it incomplete with standard gradient-based real-time and recurrent neural network. To solve this problem, our proposed method is we will doing in the three steps. That first, we will substitute this derivative, discontinuous by using the seven different smoothing technique method to make it smoothing so it can be differentiable. And the second is we will reshape this non the non-smooth landscape into a continuously differentiable sticky convex optimization problem. And from then, when we have these two condition met, we can to build the gradient-based dual dynamic to solve this problem. And from this to the next session to deal with the non-differentiable of the loss function, the non-smooth generalized pinball loss, we can rewrite it as a path function as it shown in equation 6. To replace this, we symmetrically apply the 7 distinct smoothing approximation as we denote it in the field of UI and kappa as approximate of the maximi of UI and 0. And for example, our first method is the precise penalty formulation as a phi 1. We use a smooth four-order polynomial segment within the localized body defined by a continuous smoothing parameter, and the kappa will be used to control this condition when the residual leaves this boundary is smoothly become smooth and back it to standard linear loss function. And from here is the author smoothing that you can see that is similar to the first one, and for each author that is used the polynomial, but for the phi 2 is only using square order, which is more simple to computation. And from here is the order tree that's also the similar to the uh, four author smoothing that I show you. And from here we demonstrate that this framework is truly unified on 7 different smoothing functions that we choose in. And we can show the behavior of it by this visualization. As you can see from the figure 1 is a zigzag pinball loss. That it can see that it uh, uh, non-differentiable and it's non smooth. As you can see when it's go down and back to 0 and go back to linear. From here, it's not smooth. We show the behavior when we apply the smoothing function with the different kappa from this figure 2 is on the kappa 0.2. As you can see that when the kappa is very low value, it's close to the exact generalized pinball loss. And when we increase the kappa value, it will become far from the exact pinball loss, but it will be more smoother when we add the more kappa value. Now let's discuss the architecture. Make sure that this smoothing technique by swapping out the non-smooth loss for our smooth approximation. The previously is constraint complex optimization problem. Transform it into strictly convex, completely unconstrained objective function as is seen in equation 14. From this offer a massive hardware and computational advantage. From previously, probabilistic neural network that requires solving a constraint dual quadratic programming, which means it's tracking both primal and dual variable, exploring the neural network through 3n neural, where n is the number of samples. But our formulation bypass the objective operator entirely, reduce this network structure into m plus 1 neural, where m is a feature dimension. Next, we concatenate the weight and bias term into the omega 3 and for those feature of the value into the mu tilde. Ensure that all of omega and mu have the same dimension. And we construct the continuous time recurrent neural network shown in this equation 15. Here the dynamical convergence is scaled by the eta that when we increase this value, it will be uh, let's say how fast we want it to convert. When it's more, it will convert to equilibrium point faster. And and for equation 16 is the initial point. From this, it can be seamlessly implemented by using the hardware the the hardware component to compute this real-time gradient-based neural network model. Before we deploying any neural network solver, we must guarantee it from the theory to make it more reliable. To do this, we prove three theorems. And the first one, we guarantee that for any initial points, our system can find an extent and uniqueness of the equilibrium point. And in theorem 3.2, we prove an equivalence between the equilibrium point and optimal uh, optimal solution. That a point is an equilibrium point of our dynamical system if and only if this is the unique global minimizer of our deterministic smooth objective function from equation 14. And here the theorem 3.3 where we provide to prove the convergent and global asymptotic stability. We provide our core stability proof that ensure that the system is globally asymptotically stable by designing a positive, definite, rapidly unbound candidate Lyapunov function. We show that its time derivative is strictly less than or equal to zero. Due to the strictly convexity of our smooth objective, the derivative only hits the zero when the network exactly reaches the ideal state at the core omega star. Applying Russell invariance principle confirms that every single solution trajectory is guaranteed to smoothly converge to the absolute global optimum, completely free from parameter-dependent approximation. And here is the numerical simulation. The first we do it on the synthetic dataset that we have generated 1000 data points to build up the model in different smoothing techniques. As you can see from this table, from each method, it shows that it does have many different compared to each author. And here is the trajectory visualization that we show that when we start at the many initial point on the weight and bias term, you can see that it converges to the same equilibrium point. From here is a guarantee of the uniqueness and existence of the model. And on the outer feature is the Lyapunov function that is have declared equals to zero. And from here is the detection boundary and the confusion metric of our model in synthetic dataset. From here, we don't see any difference when compared to each other. So we move it to UCI dataset. From here, we use the five datasets to compare from each author. And the last two of them, we will compare is on the existing model. When we got the chosen smoothing technique. From here in the iris and y dataset, it does not show any difference, but it can see and as in the time of computational time that it have been variant about this 0 and 1 second about this. And from the author data set that have a small huge of feature and the data point, it can show how different from them from each author. That you can see from the last one in the Stalog dataset is in the method 4. You can see that it have a less computational time, but when compared to V7, and the metric that is got have been the best when compared to each other. So this method 4 will be the choosing of our smoothing technique for this proposed work to compare to the existing model. But first we have to check the robustness to feature the noise of this smoothing technique. We have been using the same UCI dataset with the difference of noise level on the Gaussian noise when compared to its different sigma on it. From here, you can see that when the noise have been increased, it does not have effect, less, very small effect on the performance of the model. From here, you can see on the Stalog dataset that when some noise may be only effect on the computational time that have been a lot more tense time or 2 times when to build the model. And from here is the comparison on the existing model when we using the method, the V4 on the model. From here is the ID data set that we have the many model that can have the same performance. But on the hard data set, our proposed model has been get a better metric from compared to each other. But in some dataset, like ionosphere dataset, you can see that the model is neural network have still have got a better model in terms of computational time and those metrics. And from here is the visualization that we show you on the trajectory of the model on the UCI dataset that you can see that the weight of the model converts on very fast in terms of the weight and bias term. And the Lyapunov function is also declared close to 0. And figure 12 is showing that when we have start at many initial point, it still convert to the same point at the equilibrium point to confirm about the uniqueness and existence of the solution. And from here is the auto visualization on Stalog dataset, which is the same. And from all those numerical results, we come up with the conclusion that it shows the insensitivity to noise that the proposed unified smoothing framework demonstrates remarkable operational robustness under the induced Gaussian noise. And on the spec dataset, the largest performance gap between the noise-free baseline and the maximum noise level, the accuracy is only reduced as 1.5%. This maximum observed drop is fully enveloped by the model standard deviation margin. And finally, the architecture efficiency, that's the M+1 primal neural architecture, drastically reduce the computational overhead compared to the multivariable dual projection framework, cleanly securing deterministic constraint agent the outlier. And thank you everyone for your attention.